Welcome to another training provided by AI Central Lab. In this session, we'll unpack conflict-based search, an optimal algorithm for multi-agent pathfinding. Let's begin with the problem itself. Multi-agent pathfinding, or MAPF, asks how to route many agents through a shared environment at the same time. Formally, we're given a graph, usually a grid, and a team of agents. Each agent has its own start cell and its own goal cell. Time advances in discrete steps. At every step, an agent may move to a neighboring cell or wait in place. The task is to find a path for every agent so that none of them ever collide, while keeping the total cost as small as possible. Here's a tempting shortcut. Plan each agent independently, ignoring all the others. Give each one its own shortest path. It's fast and simple, but watch closely. At time step 2, both agents want the very same cell. That's a collision, and the two plans are incompatible. So why not just search all agents jointly as a single combined planner? That would be optimal, but the joint state space explodes. With more agents, the number of states grows exponentially. Before we can fix collisions, we need to name them. CBS reasons about two kinds of conflict. The first is a vertex conflict. Two agents occupy the same cell at the same time step. The second is an edge conflict, also called a swap. Two agents trade places across the same edge in one step. Each conflict is written as a tuple, the agents involved, the location, and the time. That tuple is exactly what CBS resolves. CBS attacks this with two searches stacked on top of each other. The high-level searches over sets of constraints. We'll call it the constraint tree. The low-level plans a single agent at a time, finding its shortest path that respects those constraints. The high level never touches individual moves, and the low level never worries about other agents. Together, they're powerful. Let's look at the low level more closely. It's an A-star search through space and time. A state isn't just a cell. It's a cell plus a time step. Waiting is a legal action that advances time. A constraint simply forbids one agent from one cell at one specific time. The search then plans around it. The result is the shortest path for that single agent that satisfies every constraint it has been given. Now let's run the full algorithm on our two agents. We begin at the root of the constraint tree, with no constraints at all. Each agent gets its shortest path, ignoring the other. The total cost is 8. Now we validate, replay the paths, and look for the first conflict. There it is. Agents A and B both occupy cell 2-2 at time 2. A vertex conflict. CBS resolves it by branching, creating two child nodes. Each adds a single new constraint. The left child forbids agent A from that cell at that time. The right child forbids agent B. Both inherit the root's constraints. Let's expand the left child. We replan only agent A under its new constraint. Agent A now waits one step before proceeding. Its path is one move longer, so the cost rises from 8 to 9. We validate again. This time, the paths never share a cell at the same time. No conflict remains. And because CBS always expands the lowest cost node first, this conflict-free solution is guaranteed optimal. Let's capture the whole procedure as pseudocode. Seed the root, plan every agent, and push it into a priority queue ordered by cost. Then loop, pop the cheapest node and validate its paths. If there's no conflict, return it. That's your optimal solution. Otherwise, branch into two constrained children, replan each with the low level, and push them back into the queue. Why does this work? Two guarantees make CBS special. It's optimal, because the high level is a best first search on cost. The first goal node it reaches has the minimum possible cost. It's complete. If a solution exists, CBS will find one. If none exists, it will report failure. And unlike searching the joint space directly, CBS only branches when there's an actual conflict, so easy instances stay cheap. CBS is also a foundation. Many powerful variants build directly on it. Improved CBS chooses smarter conflicts to split on, shrinking the search tree dramatically. CBS with heuristics adds admissible heuristics to the high level to guide its search. And eCBS, a bounded suboptimal version, trades a little optimality for a large gain in speed on big problems. Where does all this matter? Anywhere many agents must share tight space. Automated warehouses coordinate hundreds of robots fetching shelves without gridlock. Automated ports, drone fleets, and the crowds in video games all rely on multi-agent pathfinding. So, to recap, CBS in 4 moves: plan, validate, branch, and expand the cheapest node. One conflict, one constraint at a time. That's conflict-based search, optimal, complete, and elegantly simple. Thanks for learning with AI Central Lab. Find more trainings at www.aicentrallab.com.